It's hard to explain the automotive legend that is the Nissan GT-R Skyline, a street-legal car capable of outperforming supercars costing 3 times its price. So dominant that it earned the nickname Godzilla after demolishing the competition in Australian touring car racing. It accelerated so violently that the engineers had to develop an entirely new all-wheel drive system just to keep the car from tearing itself apart. A completely revolutionary transmission was needed to handle the brutal torque while shifting faster than any human could ever achieve. A car so advanced that when it lined up against Porsches and Ferraris on the track, its response was simply to vanish into the distance. Even though those supercars had similar power outputs, they couldn't match the technological sophistication and grip the GT-R could deploy. This allowed the GT-R to dominate racetracks across the world, humiliating cars that cost twice as much, despite many attempts to dethrone it. The entire car was built around a philosophy of total mechanical grip and lightning-fast response, which alone was a miracle of engineering design. For one, no traditional automatic transmission could handle the instant throttle response and violent acceleration this car demanded. Yet, this car was powered by a twin-turbocharged VR38 DETT engine producing 480 horsepower. But get this, the transmission attached to it could shift in just 0.15 seconds, a speed at which the GT-R could execute gear changes faster than you could blink. How on earth did it manage that? In order to achieve those kinds of shift speeds, a dual-clutch transmission was absolutely needed. A dual-clutch transmission, as you can probably guess from the name, relies on 2 separate clutches to operate. Think of it like having 2 gearboxes working in parallel inside one housing. One clutch handles the odd-numbered gears, 1st, 3rd, 5th, and 7th, while the second clutch manages the even-numbered gears, 2nd, 4th, and 6th. Here's where the genius comes in. While you're accelerating in 3rd gear, the transmission has already pre-selected 4th gear on the 2nd shaft. The instant you need to shift, the 1st clutch releases 3rd gear while simultaneously the 2nd clutch engages 4th gear. With both clutches working in perfect coordination, there's virtually no interruption in power delivery. The engine stays connected to the wheels throughout the entire shift, with computer-controlled precision. This type of transmission is capable of changing gears far faster than any manual gearbox or conventional automatic, but it required revolutionary engineering to handle the GT-R's savage power output. The GR6 dual-clutch transmission of the GT-R is nestled between the engine at the front and the rear differential. But get this, in most cars, the transmission sits right behind the engine. Not in the GT-R. The engineers placed the transmission at the rear axle in what's called a transaxle configuration. This wasn't just for show, it was critical engineering. First, the weight distribution. By moving the heavy transmission to the rear, the GT-R achieves a near-perfect 53% front, 47% rear weight distribution. This keeps the car balanced under acceleration, braking, and cornering. It also means that when the rear-mounted transmission dumps power into the rear differential, the response is instantaneous with minimal drivetrain loss. The transmission connects to the engine through a carbon fiber driveshaft spinning at engine speed. This driveshaft had to be incredibly strong yet lightweight because it's constantly transmitting over 430 lb-ft of torque from the front to the back of the car. Carbon fiber was the only material that could survive the torsional stress while keeping the rotational inertia low enough for instant throttle response. Around the transmission, there's a sophisticated oil cooling system, which takes oil from the gearbox and routes it through dedicated coolers. This oil was used to keep the clutch packs from overheating during violent acceleration runs, which again improved transmission longevity and allowed the car to perform at its peak repeatedly. After the oil passes through the coolers, it returns to the transmission, maintaining optimal operating temperature even during back-to-back launches. The transmission itself uses wet multi-plate clutches rather than the dry clutches found in many dual-clutch systems. Why? Because dry clutches overheat and fail under the kind of punishment GT-R owners dish out. The wet clutches are bathed in oil, which dissipates heat far more effectively. This allows the GT-R to execute launch after launch without the clutches glazing or warping. But the transmission was only half the story. The real magic happened in how the GT-R managed power delivery to all 4 wheels. Most all-wheel drive systems are reactive. They wait for wheels to slip, then send power to wherever grip exists. But by the time that happens, you've already lost precious traction and time. The GTR's Atessa ETS Pro all-wheel drive system is predictive. It doesn't wait for wheel spin. It anticipates it. The system uses a wet multi-plate clutch pack located in the front differential housing. This clutch can vary the torque split between the front and rear wheels infinitely between 0 to 100 and 50-50. Under normal driving, the GTR operates as a rear-wheel drive car, sending 100% of the power to the rear wheels for that engaging, sporty feel. But the moment the onboard computer detects that you're about to lose traction, analyzing throttle position, yaw rate, steering angle, lateral g-forces, and wheel speeds 100 times per second, it preemptively engages the front clutch pack. In just 0.1 seconds, the system can redirect up to 50% of the engine's torque to the front wheels. This happens before you even feel the car start to slide. The result? Absolutely devastating corner exit speeds. While rear-wheel drive supercars are dancing on the edge of traction, the GTR is already rocketing toward the next corner with all 4 tires clawing at the pavement. The system is so responsive that it can adjust torque distribution mid-corner. If you're entering a turn and the front tires need more grip, the system reduces front torque. As you hit the apex and prepare to accelerate out, it seamlessly transitions to sending power rearward, then instantly redistributes forward as the rear approaches its limit. This constant rebalancing happens faster than any human could process, let alone react to. These bypass clutches and electronic controls played a critical role in maintaining grip levels. If this was mismanaged, the car would simply understeer into a wall or snap into oversteer, resulting in sudden loss of control, which would cause the car to violently spin in whatever direction physics decided. If this happened, the system would instantly redistribute torque, modulate brake pressure to individual wheels through the vehicle dynamics control system, and get the car back to its optimal slip angle. Besides this torque distribution system that managed power between front and rear, there was also an active rear limited slip differential that distributed power between the left and right rear wheels. This differential was the primary mechanism that transformed the car from merely fast into absolutely alien. Limited slip differentials are great. They significantly improve cornering without needing a whole lot of additional weight. They basically lock the rear wheels together when needed, forcing both to rotate at the same speed to prevent inside wheel spin during hard cornering. But they need to be carefully calibrated. However, as the cornering forces increase, they become the only feasible way to generate the kind of rotation and adjustability needed to set lap records. And they do gain effectiveness thanks to the massive Bilstein Damptronic suspension providing incredible body control. The crazy thing about the GTR, however, is that the engineers could have eked out more performance from this chassis to increase the top speed even more. The GTR could theoretically exceed its electronically limited 196 mph top speed. So why did they stop at 196 mph? Would they have run out of tire capability? The tires on the GTR are specifically developed Dunlop SP Sport, Max GT600 run flats, massive 255 40R20 fronts, and 285 35R20 rears. These aren't your average road tires. They were co-developed with Nissan specifically for the GTR's performance envelope. But tires have speed ratings, and beyond certain velocities, the centrifugal forces and heat buildup can cause catastrophic failure. The GTR's tires are Y-rated, meaning they're certified safe up to 186 mph. Nissan added a 10 mph buffer and called it a day at 196 mph. Could they have fitted different tires? Absolutely. But there's a deeper engineering reality at play here. Aerodynamic drag increases with the square of velocity. At 196 mph, the GTR is already pushing through the air with tremendous force. To go faster would require exponentially more power, and more importantly, the cooling systems for the engine, transmission, differentials, and brakes would need complete redesign. The GTR wasn't built to be a top-speed monster. It was built to annihilate anything in its path on a racetrack, where top speed matters far less than acceleration, braking, and cornering. This car, like a Le Mans prototype, was actually designed around the racetrack first and street legality second. Its dry weight was approximately 1,740 kilograms. With fluids, you're looking at around 1,850 kilograms. That's heavy by sports car standards. But here's the thing. Every single kilogram served a purpose. The GTR uses a body structure Nissan calls Premium Midship Platform. The engine sits as far back in the chassis as possible, The transmission is at the rear axle, and the fuel tank sits in the middle. This creates a centralized mass that reduces polar moment of inertia. Basically, it makes the car rotate more willingly in corners despite its weight. Even then, without the sophisticated electronic systems managing every aspect of the car's dynamics, this platform would have been nearly impossible to drive at the limit. Weight distribution varied depending on fuel load. A fully loaded GTR had nearly perfect 53-47 front-to-rear balance, but as fuel burned off during a track session, that shifted rearward slightly. The GTR's computers compensated in real time, adjusting torque split, differential lock percentage, and even damper firmness to maintain optimal handling characteristics regardless of fuel level. And of course, the handling was severely affected by suspension setup and tire pressures. But on average, the GTR could pull 1.0 G of lateral acceleration on street tires. On a proper racetrack with sticky rubber, over 1.2 G sustained. About enough grip to make your vision blur and your neck muscles scream. Not terribly common for a street-legal production car. Most supercars of that era struggled to match it. However, the GTR achieved this through more than just all-wheel drive and fancy differentials. The suspension geometry itself was revolutionary. So, if it wasn't just the drivetrain and electronics that made the GTR dominant, what else contributed? At speed, the GTR's body generates significant aerodynamic downforce. The front bumper channels air through carefully sculpted intakes, cooling the brakes and engine while generating a low-pressure zone underneath. The flat underbody panels extend all the way to the rear diffuser, which accelerates air out from under the car, creating suction that pulls the GTR onto the road surface. The rear wing isn't just for show. It's adjustable and generates real downforce. At the GTR's top speed, the combined aero generates roughly 100 kilos of downforce. That might not sound like much compared to dedicated race cars, but remember, this is a street car with air conditioning, a stereo, and a back seat. The aerodynamic efficiency is remarkable for something you can daily drive. This is what truly enabled the GTR to humiliate more expensive machinery. Without careful aerodynamic development and active management systems, the car would simply understeer off-track or become unstable at high speeds. Even the cooling system needed to be specially engineered to handle the heat generated during full-throttle track sessions. The twin-turbo VR38D ETT engine produces incredible heat, not just from combustion, but from the turbochargers themselves, which glow red-hot under heavy use. Nissan installed massive intercoolers in the front bumper to cool the compressed air from the turbos before it enters the engine. Cooler air is denser, which means more oxygen molecules per cubic centimeter, which means more power. The intercoolers are so large they actually hurt the car's aerodynamics slightly, but the power gain is worth the trade-off. The engine oil and coolant systems are similarly oversized. Dual oil coolers ensure that even after 20 consecutive laps at Nürburgring, the oil temperature stays within operational limits. The engine coolant flows through a radiator large enough to cool a much larger engine. Because the engineers knew GTR owners would push this car far beyond what typical sports car buyers do. The cooling air intake at the front splits into multiple paths. Some goes to the radiator, some to the intercoolers, some to the transmission cooler at the rear, and some to the brake ducts. Managing all these airflows without creating drag or lift required thousands of hours in the wind tunnel. One huge question I had about the GTR was why Nissan chose a twin-turbo V6 instead of a V8 or V10 like their competitors used. If Honda used a V10 in the NSX and Lexus used a V10 in the LFA, why not Nissan? The GTR's VR38 DETT is a 3.8-liter V6 with twin turbochargers, producing 480 horsepower in stock form. But here's the genius. This engine is massively over-engineered. The block is cast iron in some versions, forged in others. The internals are strong enough to handle over 1,000 horsepower with relatively simple modifications. Why a V6? Packaging and weight distribution. A V6 is significantly shorter than a V8 or V10, which allowed Nissan to mount it further back in the chassis, behind the front axle line. This contributes to that optimal weight distribution. The engine sits so far back that there's barely room for your hand between the firewall and the valve covers. The twin-turbo configuration provides massive torque across the entire rev range. Peak torque of 434 lb-ft arrives at just 3,200 RPM and stays flat until 5,800 RPM. That's a 2,600 RPM power band. where you have maximum torque available. By comparison, naturally aspirated V8s and V10s need to scream to 8,000 plus RPM to make their power, and their torque curves are far less flat. Turbochargers also provide something naturally aspirated engines can't: scalability. GTR owners routinely tune their cars to 600, 700, even 200 plus horsepower with upgraded turbos, fuel systems, and engine management. The aftermarket for GTR performance is massive because Nissan built a platform that could handle it. But turbos have their downsides: lag, heat, and complexity. Nissan minimized lag by using twin turbos instead of a single large one. Each turbo only needs to spool up for 3 cylinders, so they respond far quicker than a single unit trying to feed all 6. The turbos are integrated into the exhaust manifolds, reducing the distance hot exhaust gases need to travel before hitting the turbine wheels. This shortens spool time even further. By 2,000 RPM, you're already building boost. By 3,000 RPM, you're in the full torque band and being shoved back into your seat. These efforts helped make the engine responsive, but the fuel system still needed to be incredibly precise. The GTR uses direct fuel injection, where fuel is sprayed directly into the combustion chamber at extremely high pressure, around 2,000 psi. Direct injection allows for more precise fuel metering, which improves combustion efficiency and power output. It also allows the engine to run higher compression ratios without detonating, because the fuel has a cooling effect inside the cylinder. The GTR runs 9.0.1 compression, which is relatively low for a modern engine, but that's because of the forced induction. The turbos are doing the work of compression externally. The fuel injectors fire multiple times per combustion cycle, a technique called split injection. This optimizes the fuel-air mixture for maximum power while minimizing emissions. It's the kind of technology you'd expect in a modern diesel engine, applied to a high-performance gasoline engine. Really, the GTR's engineering philosophy was about leaving no performance on the table. Every system was optimized, every component tested to destruction and redesigned, every possible advantage exploited. So, if it wasn't the engine or transmission or aerodynamics that limited the GTR's ultimate capability, what did? The driver. Nissan's engineers realized early on that human reflexes simply couldn't keep up with what this car was capable of. So they built systems to compensate. The 3-mode vehicle dynamics control system, normal, R mode, and off, progressively removes the safety nets. But even in R mode, the car is still making thousands of micro adjustments you'll never notice. In normal mode, the car is civilized, compliant, almost docile. The transmission shifts smoothly, the suspension soaks up bumps, and the torque delivery is linear and predictable. You could hand the keys to your grandmother. Switch to R mode, which stands for race, and everything changes. The dampers stiffen, the throttle response sharpens, the transmission bangs through gears violently, and the stability control loosens its grip just enough to let you slide the car if you're skilled enough. The car transforms from a luxury GT into a weapon. Turn everything off and you're on your own. The GTR will still send power to all 4 wheels through its mechanical all-wheel drive system, but it won't save you from your mistakes. There's no electronic safety net, no computer watching the yaw rate and adjusting brake pressure, no stability control gently pulling you back from the edge. This mode is for professional drivers and brave fools. What's remarkable is that even in this fully disabled state, the GTR remains surprisingly manageable thanks to its fundamental mechanical balance. The ATISA system still operates mechanically, sending power forward when the rear wheels slip, but without the electronic precision of the normal modes. You can feel the car's weight shifting, feel the rear end starting to slide, and catch it with steering input and throttle control. It's raw, visceral, and absolutely terrifying at speed. Professional drivers who've tested the GTR in R mode report that it feels like a completely different car. The mechanical grip is still there. Those massive tires and that sophisticated suspension don't disappear, but suddenly you're responsible for managing every input. The car becomes more involving, more demanding, and paradoxically more rewarding when you get it right. The sophistication of these systems is what allowed automotive journalists to lap the Nürburgring in under 7 minutes and 30 seconds in a bone-stock GTR, a time that embarrassed supercars costing $300,000 or more. To put this in perspective, a Porsche Carrera GT, which cost $448,000 when new, managed 7 minutes 32 seconds. A Ferrari Enzo at $660,000 posted 7 minutes 25 seconds. The GTR, at less than 1/6 the price of the Enzo, was within 7 seconds. Porsche was reportedly furious, claiming Nissan must have used a specially prepared car. They sent their own engineers to examine the test vehicle, looking for modifications, tuned suspension, stickier tires, anything that might explain the performance gap. They hadn't found anything. They just built something better. The GTR's Nürburgring time wasn't a fluke or a one-off achievement. Multiple automotive publications replicated similar times. Sport Auto magazine in Germany achieved 7 minutes 29 seconds. Best Motoring in Japan posted 7 minutes 27 seconds. These times were achieved by professional racing drivers, but they were achieved in completely stock cars pulled directly from dealership inventory. What made this even more embarrassing for the competition was that the GTR achieved these times while being easier to drive fast than any of its rivals. The Ferrari Enzo required expert throttle control and supreme confidence to extract maximum performance. The Porsche Carrera GT was notoriously difficult to drive at the limit, with several high-profile crashes attributed to its unforgiving handling characteristics. The GTR? You could drive it hard right out of the box, and the electronics would help you look like a hero. This democratization of performance was precisely what Nissan intended. They wanted the GTR to be fast in anyone's hands, not just professional racing drivers. The electronics didn't make the car boring or numb. They made it accessible. They allowed drivers to explore closer to the actual limits of the car's performance without the constant fear of catastrophic mistakes. Today, engineers have made huge strides in hybrid powertrains and electric motors, and the automotive landscape has shifted dramatically since the R35 GTR launched in 2007. The GTR used purely mechanical and electronic systems to achieve its performance,